Good morning, everybody. Sorry I'm not able to be in school today. Not feeling the best. Hope to be back on Friday, even though you don't see me on Fridays. I'm going to go through the notes for today. You can watch these, if you can watch these videos at like 1 1/4 speed, 1 1/2 speed. That might make sense for some of you. It might make sense a little quicker for some of you. So feel free to do that with the rest of the class period. Should work on finishing LT 26 homework that's due tonight, and then start or finish LT 27 homework that is due Sunday. Feel free to work together. I don't know if watching the video all together is something you'd want to do, but like if everybody at school wants to watch the video at the same time, and or people on Zoom, whatever makes sense for everybody. So LT27, our last learning target before we are taking our quiz, and again, our quiz is going to be sometime next week, is about the difference between linear, quadratic, and exponential relationships. The very first picture, the top page 1, gives you an idea of what these graphs look like. We know what a line looks like. We know what a quadratic function looks like. It looks like a parabola. Then we have this exponential function. Exponential functions will give you like more of a detailed picture, kind of in general look like this. Kind of looks almost maybe like a parabola that you took one side and kind of like shoved down so it gets flatter as it goes on, something like that. We're going to talk about tables. It's been a little while since we've talked about tables and looking for these relationships. We've already actually done linear. It's been a couple months, but we've done these before. If the x changes at the same rate, so you see our x values go up by 1 and 1 and 1 and 1, how do we know the relationship is linear? Linear is going to be an equal increase or decrease, or same change. So the number that it changes by can be different, but if all the x's values change by the same number and all the y values also change by a same number, then we know it's going to be linear. So how do we get from -1 to 2? We add 3. How do we get from 2 to 5? We add 3. How do we get from 5 to 8? We add 3. How do we get from 8 to 11? We add 3. When we look, we see all those are the same. We see all those the same. You might recall that we talked about this in terms of slope. Slope is going to be rise over run. You can also think about it as the change in y over the change in x. It's very easy to see in this that every time y changes by 3, x changes by 1. So this table can show us that we have a slope of 3. This is a linear relationship. Now quadratic, we've never specifically looked at this, but take a look at this table. We're going to start the same way. We're going to see how the y's change. How do we get from 1 to -1? Well, that requires you to subtract 2. How do you get from -1 to 1? You have to add 2. How about from 1 to 7? You have to add 6. And how about from 7 to 17? You have to add 10. So some things to notice here. The x's are changing at the same rate still. The x's are remaining constant in their change. But the y change isn't constant. It's different each time. It's -2, and then it's +2, and then it's +6, and then it's 10. So what else can we look for to figure out that it's quadratic? For quadratics, we're going to look at the second difference. Now, what the heck am I talking about there? Sorry, my handwriting is not looking so great. Second difference, difference. If you look at the difference from -2 to 2, well, that's +4. And if you look at the difference from +2 to +6, that's +4. If you look at the difference from 6 to 10, you'll see that's +4. If you see that constant change in the second difference, that is going to be how we can tell we have our quadratic relationship. Linear, you're going to see it in the first difference. Quadratic, you're going to see it in the second. So determine if the following tables represent linear or quadratic. I think it would be a good moment to pause for a sec, go through the tables. Remember, if you go through, all the x's are just changing by the same, then we look at the y's. If the y changes the same every time, it's going to be linear. If it's not, but you look at the difference of the differences, and that's the same, then it's going to be quadratic. So you pause your video right now. I'm going to work on this. When you unpause, you can see me work this out. So I start with the x's. I look and I see it. They're all +1. It's good. Don't have to worry about anything funky happening here. How do we get from 9 to 5? We have to subtract 4. How do we get from 5 to 1? We have to subtract 4. How do we get from 1 to -3? We have to subtract 4. Excuse me. How do we get from -3 to -7? We have to subtract 4. We see this same first difference for the y, x's the same. This table represents a linear relationship. First difference is all the same. Looking at the second table, again, the y's, the x's, you're adding 1 every time. Don't really have to give that too much thought. That's nice. Let's look at how our y's change. From 48 to 30, that's down 18. From 30 to 16, that's down 14. From 16 to 6, that's down 10. And 6 to 0, that's down 6. Now, it's easy to tell it's not linear because these changes are not the same while these are. And what do we know how to do? We can check to see it's linear. It might be just nothing. It might not have a relationship. That's always a possibility. Everything isn't just linear or quadratic. Sometimes tables are just tables and they just have random numbers in them. But if we check the second difference, -18 to -14, that's +4. -14 to -10, that's also +4. -10 to -6, that's +4. And we see this second difference is the same. Therefore, we would say that this table represents a quadratic relationship. So hopefully you got that. On page 3 here, why is this table different? So we're going to go through and do the same thing. We're going to look at how things are changing. +1, +1, +1, +1. So all the x's are still just adding 1. When we go over to our table 1 to 3, we're adding 2. 3 to 9, we're adding 6. 9 to 27, we're adding 18. And 27 to 81, we are adding, oh boy, mental math at 5:30 in the morning. 54. Does that look right? Yeah, I think that's right. So it's not linear. We look at the second difference. 2 to 6 is +4. 6 to 18 is +12. 18 to 54. Oh, again, I got to think about this one. Is that 36? The second difference isn't also the same. Doesn't have a quadratic pattern. Maybe your next thought is like, let's go to the third difference then. 4 to 12 is 8. 12 to 36 is 24. They're still not the same, and we're kind of running out of space to kind of see these relationships. But we've kind of stumbled upon nothing. So a question I'm going to ask you is, do you notice a pattern? So I want you to kind of get out of the mindset of what we've been doing for 10 minutes here and relook at these y values. 1, 3, 9, 27, 81. Is there something else that you know about these numbers? My hope is yes. When you see 3 and 9 and 27 and 81, it's supposed to remind you of something. Well, I'll spoil it if you can't think of it. Another way to get from 1 to 3 that isn't adding is we can multiply. What if we multiplied by 3? 1 times 3 is 3. What if we multiplied by 3? 3 times 3 is 9. What if we multiplied by 3? 9 times 3 is 27. What if we multiplied by 3? 27 times 3 is 81. So there isn't an adding and subtracting pattern. There's a pattern that requires multiplication. So we have a different kind of pattern that we can be looking for. Try to figure out the pattern of this one down below for a second. So I think it'd be a good idea to pause your video for a minute or two, give you the X pattern. I want you to think about the Y pattern, and I want you to think about this. So pause for a sec, come back when you're ready. I'll start. Sometimes these can be a little tricky. Maybe I'll start with one that makes a lot more sense to me. I can either add 1 to get from 1 to 2, or I can multiply by 2. Let's see if the multiplication works. How can I get from 2 to 4? I can multiply by 2. How do I get from a half to 1? If you multiply a half by 2, you get 1. If I have a quarter and I want 50 cents, aka 2 quarters, I can multiply by 2. So this table is going to have this pattern where all the y values are a multiple 2 of another. So that kind of relationship, I guess I don't remember if I wanted to say this here or not. Maybe I'll say it. This is going to be our exponential relationship. Exponential is going to be that one that you see the multiplying pattern. It's not supposed to be an F, that's supposed to be a T. Here on page 4, I want you to graph these points. So I'm going to do it, but if you want to do it before me, pause and do it yourself. 0, 1 is just 1 up, 1, 2 is right 1 and up 2, 2, 4 is right 2 and up 4, 3 and 8, 4 and 16. So when you look at this graph, one thing I can tell is it's not a line. I guess maybe it could look like a parabola if it was mirrored on the part that we can't see. But what if we looked at this table to try to help us out and say, is this half of a parabola, or maybe it's that interesting looking exponential graph? 1 to 2, we can add 1. 2 to 4, we can add 2. 4 to 8, we can add 4. 8 to 16, we can add 8. 1 to 2, we can add 1. 2 to 4, we can add 2. 4 to 8, we can add 4. Do you see how this pattern is repeating? 1 to 2, we can add 1. 2 to 4, we can add 2. See, this pattern just repeats itself over and over and over again. It's not going to get us anywhere. The first difference isn't the same. The second difference isn't the same. So if you do that, you should go back and check to see if it's exponential. You think about multiplication instead of addition or subtraction. How else can we get from 1 to 2? We can multiply by 2. And then 2 to 4, we can multiply by 2. 4 to 8, multiply by 2. 8 to 16, multiply by 2. This is going to be exponential. If we were to see the rest of this graph, it's actually going to kind of curtail off and become like flat almost. So we'll not go back upwards like a parabola might. All right, we're going to do the same thing, but we're going to take some points and just plug them in to our table. 1, 4, 2, 5, 3, 4, 4, 1, 5, -4. So all the x's go up by 1s. It's good. We don't have to think about any crazy stuff. That's different. Let's look at our y table. Let's check for our first differences. 1 to 5, or excuse me, 4 to 5, we have to add 1. 5 to 4, we have to subtract 1. 4 to 1, we have to subtract 3. 1 to -4, we have to subtract 5. It's not linear. The first difference is not all the same. Second difference, 1 to -1, that's 2 smaller. 1 to -3, that's 2 smaller. -3, -5, that's 2 smaller. Look there. That is our second difference being the same, meaning that this thing is going to be quadratic. Graphing our points. 1, 4, 2, 5, 3, 4, 4, 1, 5, -4. Can't really draw it perfectly, but given our points, here's what we have. And if I were to continue this on the other side over here, you can kind of guess that it's going to look a bit like that. You'll see it actually turn around. We can see this turning around. The exponential graph doesn't turn around. It doesn't like go from up to down and then back up, those kind of things. All right, we're rocking and rolling, almost done. The data in the table give the value of a used car over time. Which type of function models the data best? You're just looking for roughly our patterns. I always check linear first and quadratic. Now, these numbers and the way I'm feeling and how early it is in the morning, I'm going to grab a calculator. What's the difference between 12,575 and 11,065? I'm going to subtract them. So 12,575 minus 11,065. That is down 1,510. I'm going to take my 9,750 and subtract 11,065. That's going to be down 1,350, 15, sorry. And then 8,520 minus 9,750 is negative 12,030. And then 7,540 minus 8,520, that's a negative 980. It's not linear. It's not linear. So we check our second difference. So I'm going to take negative 1,315, subtract negative 1,510, and I get, this is 195 bigger. Well, negative 1,013 is a bigger than 1,510 by 195. And I take negative 1,230 and I subtract negative 1,315, and we get 85. And then I do negative 980 minus negative 12 or 1,230, and we get plus 250. So you will see our second difference, also not the same, which leads me to believe, that this might be exponential. But how can we do this exponentially when we can't look at these numbers and kind of say, oh, we're multiplying by 2 or by 3? We're actually going to use division to try to help us out and see what we get. So first difference, very different. Second difference, very different. So let's try exponential. And if you don't know what we're multiplying by, if you noticed how I was figuring out these numbers using subtraction, we can use division to see what numbers we would do for like the multiplication stuff. So I'm going to take my top two. I'm always going to take the bottom one and divide it by the one on top. So I'm going to take 11,065 and divide by 12,575. And I get about, if I round to 2 decimal places, 0.88. It's 0.8799. So it's going to round to about 0.88. And then if I do 9,750 divided by 11,065, got to go to my calculator for that one. I get, again, if we round, about 0.88. 0.8811568,007. But this is looking promising. Doing these dividing thing, it looks like we've found the thing that we're multiplying by. I haven't left myself much space, have I? 8,520, then divided by 9,750. 8,520 divided by 9,750. This rounds to about 0.87. I know it's a little different, but given a real world model, I think that's still quite close, quite close. And then 7,450 divided by 8,520. We get about 0.88. That might actually round up to 0.89 depending on how far back you're looking, but we'll stick with that. So if we get rid of our first and second differences when we're thinking about adding and subtracting, what number do we multiply to 12,575 to get to the next one? Well, if you multiply by 0.88, you'll get about that number. And if you multiply 11,065 by about 0.88, you get about 9,750. If you multiply that by about 0.87 or 888, you get about 8,520, and then 0.88. If you multiply again, you get that thing. So it's not going to be perfect when we were thinking about real world data, but this fits an exponential pattern pretty well. Took a lot of work using division to help me figure that out. Okay. If you want to try the other table before I get there, that'd be great. Pause it, see what you come up with. I'm going to keep working because you can pause and join me when you're ready. I look at the X differences, which it's been so nice. All the examples that we're doing, they have not been different at all. It's just been our plain old getting one bigger every time. 7 to 13. 13 is 6 bigger than 7. 21 is 8 bigger than 13. 31 is 10 bigger than 21. 43 is 12 bigger than 31. It's not linear. Those are not the same. But you might notice that 8 is 2 bigger than 6. 10 is 2 bigger than 8. 12 is 2 bigger than 10. Our second difference is the same. So this would be a quadratic relationship. Quadratic. Quadratic. Sorry, my handwriting is not looking very great, guys and girls. The last 2 pages are some practice. I would probably say pause, try some out, see if you can get it. I'm going to go a little bit quicker through it. So I've kind of showed you all the tips and tricks that you'd need to figure things out. But here I go. I'm not going to write the X difference because they're the same in number 7. Negative 11 is 1 bigger than negative 12. Negative 8 is 3 bigger than negative 11. Negative 3 is 5 bigger than negative 8, and 4 is 7 bigger. These are not the same, so it's not linear. But if you look at the second difference, 3 is 2 bigger than 1. 5 is 2 bigger than 3. 7 is 2 bigger than 5. Quadratic. No. Something like 8, you don't have to write it in a table like this, but I really think that setting it up in a table is going to give you the visual cues as to what's going on and going to help you organize your thoughts. You can do it without writing this table, but I'm certainly going to suggest that you do so. 1, 4, 2, 9. The ones are going up by 1 every time, so I'm not going to write that. 0 is 1 less than 1. That's -1. 0 to 1, we have to add 1. 4 is 3 bigger than 1. 9 is 5 bigger than 4. Not linear. Those are not the same numbers. To get from -1 to 1, we have to add 2. 3 is 2 bigger, and 1, 5 is 2 bigger than 3. Here we go. Another second difference being the same. And it's quadratic. All right, got to make another table. Oh, we got some decimals. Everybody's favorite. Only 4 points though. So if you're not sure what to do, I would just start with your linear differences. How do we get from -0.25 to -0.5? Well, that's subtracting 0.25. It's going to make it more negative. How do we get from -0.5 to -1? It's going to be -0.5. How do we get from -1 to -2? We have to subtract 1. -2 is 1 smaller. So it's not linear. Look at my second difference. How do I get from -0.25 to -0.5? Well, that's -0.25. -0.5 to 1 is -0.5. We noticing something? These aren't equal. We kind of just see the same types of numbers over and over again. But our first difference didn't work. Our second difference didn't give us anything. So now it is time to think about exponential. So can we think about multiplying? What do we multiply to -1 to get -2? That would be multiplying by 2. What do we get, or how do we get from -0.5 to -1? That's another multiply by 2. If we multiply -0.25 by 2, we get -0.5. This is going to be exponential because there is a multiplicative relationship. And then our last table for the day. All the x's are all the same, so I'm not going to write anything. 1.5 is 0.5 bigger than 1. 3 is 1.5 bigger than 1.5. 5.5 is 2 bigger. 2.5, excuse me, bigger than 3. And 9 is 3.5 bigger than 5.5. Not linear because those aren't the same. 1.5 is 1 bigger than 1. 2.5 is 1 bigger than 1.5. 3.5 is 1 bigger than 2.5. You see that pattern in the second difference? That is quadratic. All right. I'm sorry that I cannot be there today. Use the rest of the time to get your LT26 homework completed, and you have the LT27 homework that is being assigned today. I think I'm going to push the due date back till Monday, just in case you have some questions. And I'll update you on anything that I decide over the weekend with quiz dates. So have a good rest of your day. Again, sorry I can't be there. Have a good weekend, and I'll see you all later.